Hello everyone, welcome to this lecture on Bootstrap confidence intervals for Stat 3150 statistical computing. So this lecture follows the previous lecture, which was on Bootstrap, and the objectives are learning how to compute the different Bootstrap confidence intervals. So we'll see there's different ways of computing confidence intervals using Bootstrap. And then having an understanding of their theoretical properties, not necessarily being able to derive them, but sort of understanding what they mean and why you would care about those theoretical properties. So far we've mostly built confidence intervals using the central limit theorem. So we were making the assumption that a normal distribution was a good approximation to the sampling distribution. And we can certainly do so with Bootstrap, just like we did with Jackknife. And using the estimate of the standard error we computed with Bootstrap. But since we're sort of sampling from the sampling distribution already, we can actually do much better. And this becomes important when you move away from confidence intervals that are built using other estimators or other statistics than the sample mean. So we're going to look at 5 different ways of constructing those confidence intervals. And so you can see the names here on the slide. There's the standard normal bootstrap, which is essentially what we've been doing so far. There's something called bootstrap percentile, the basic bootstrap, and then the student bootstrap and the BCA interval. All 5 of them have different properties, and they can all be useful depending on the context. But there's, of course, trade-offs when using one versus the other. So it's important to see all of them and know which will be most suitable for your particular application. So let's start with the first one. And as I said, this is similar to what we've been doing so far. And it relies, of course, on the central limit theorem, which is a theorem about the sample mean, or something that looks like a sample mean. So there's definitely an assumption here you need to keep in mind. But essentially what it means is that theta hat minus its expected value over its standard error will converge to a standard normal as the sample size goes to infinity. So if we estimate the bias and the standard error using Bootstrap, then we can construct an approximate confidence interval for theta using the formula here. So theta hat minus the bias, right? So we want to remove the bias as much as possible, plus or minus the standard normal critical values times the standard error of theta hat. It's very easy to compute, but of course it assumes that the sampling distribution is approximately normal, which is not necessarily the case. And in particular, when the sampling distribution is skewed, this confidence interval will not work particularly well. So let's look at the second one. So recall what we've been doing is resampling data with replacement and then recomputing the estimates. So we're getting a series of samples from the sampling distribution. Those are what we call the bootstrap estimates. So let theta hat little b be those bootstrap estimates. So what the bootstrap percentile method does is that it takes the sample quantiles from these estimates to construct a confidence interval for theta. So if we take theta hat alpha over 2 and theta hat 1 minus alpha over 2, and those are the sample quantiles from the bootstrap estimates, you can construct a confidence interval that way, using the first one as the lower bound and the second one as the upper bound. So this is very simple. You'll see later that we can do this using the quantile function in R. And it's very simple. But don't be fooled by the simplicity. Its validity actually requires some strong assumptions. And we won't go into details here because I'm going to show you better confidence intervals. But you can see, if you're interested, you can look at the extra notes I posted on UMLearn. And in particular, when the bias is very large, you can get unrealistic confidence intervals. So when there's a lot of bias, a lot of skewness, this Bootstrap percentile confidence interval is not really valid. Okay, so those were the first two, and then let's look at the third one before jumping to an example. It's called the basic Bootstrap, and it's also known as the pivotal Bootstrap confidence interval. And it's very similar to the Bootstrap percentile approach, but instead of taking the sample quantiles of theta hat b, what we're doing is instead taking the sample quantiles of the pivot quantities theta hat b minus theta hat. So we're subtracting theta hat, which is the estimate on the whole data, the original data set. We're subtracting it from all of the theta hat b's, and then taking the sample quantiles from these quantities. And so note that the beta quantile of those pivotal quantities you can actually get from the sample quantiles of just the bootstraps. You can check when you subtract a quantity like this, that's a monotone transformation, so it preserves quantiles. And so the quantiles for the pivotal quantities can be expressed in terms of the quantiles of the bootstrap samples minus theta hat. And so to build the basic bootstrap, what we do is we take theta hat minus those critical values, some critical values. But as I said, instead of using the critical values of the standard normal, we take the critical values from the pivot quantities. So we take theta hat minus theta hat beta minus theta hat. And if you do a little bit of algebra, you'll see the formula here, which is the one you typically see as part of the definition. You get 2 times theta hat minus theta hat beta. And so if you build this for a confidence interval, what you get is 2 times theta hat minus theta hat 1 minus alpha over 2, and then 2 times theta hat minus theta hat alpha over 2. Right? Remember, we're subtracting the quantiles, and so the lower quantile goes for the upper bound, and the higher quantile goes for the lower bound. So why would you use the basic over the percentile? Well, it turns out that the basic Bootstrap has better theoretical properties and stronger convergence guarantees than the percentile, and it doesn't rely on the same strong assumptions. So the basic Bootstrap confidence intervals should be preferred over percentile. Okay, so let's look at an example. We'll stick with the example we've been working on so far. So we're going to compute the 3 types of confidence intervals that we've discussed for the correlation between LSAT and GPA scores. So the code here, we've looked at that code before. First, I'm loading the package Bootstrap containing the data, and then setting b equals 5,000, and n is going to be the number of rows, so the number of observations. And next, I want to get all my Bootstrap samples and then compute the sample correlation on all those samples. So remember, we're sampling with replacement, and I'm sampling the indices here just as a shorthand. And so a sample of n, replace equals true will give me a sample with replacement of integers between 1 and n. So then I can compute the correlation between LSAT and GPA for that particular Bootstrap sample. And then, of course, row hat will be the correlation on the original data, so without resample. Next, I compute the bias and then the standard error. The bias, remember, was the sample mean of the Bootstrap estimates minus the original estimate. And the standard error is the standard deviation of those Bootstrap estimates. Again, I just want to clarify, we're not dividing by square root of n here. The dependence on square root of n is already built into our samples. Okay, so now we have all the quantities we need. Let's build the confidence intervals. So the standard normal, as you remember, is the estimate minus the bias plus or minus 1.96 times the standard error. And so we get confidence intervals going from 0.52 to 1.04. As we've already looked at this confidence interval, and we also noted that it goes over the range of possible values for the correlations. Next, for the Bootstrap percentile, we can simply use quantile to compute the sample quantiles from the Bootstrap samples. And in this case, we do get a sensible confidence interval. It goes from 0.46 to 0.96. So it doesn't go over 1. And then finally, we can compute the basic Bootstrap using, again, the same quantile values. But we're using a different formula. We're using 2 times theta hat, or rho hat, minus the critical values. And here I'm using use.names equals false. You can try removing that. If you do, you'll see that you get names for each element of the vector, and they don't really match the percentiles that we would expect. And so just to avoid confusion, I remove them by using use.names equals false. And now what we get is, again, a confidence interval that's going over the range of valid values. It goes from 0.59 to 1.1. Okay. And so we can look at them here, all 3 of them together in the table. And only the percentile method gives a sensible confidence interval. And it turns out that for this particular example, because the bias is so small, the percentile confidence interval is actually valid here. You could test that using simulation if you wanted to. Yeah. So let's move on. Oh, so yes, so here you can see a histogram of all the Bootstrap samples, and you can see that the distribution is actually skewed here. So we would not expect the standard normal Bootstrap's confidence interval to be valid here because the distribution is not symmetric. Okay. Now, so those were the first 3 confidence intervals, and they're definitely much simpler than the next 2 we're going to look at. Because the next 2 we're going to look at actually requires a second, they both require a second level of resampling, as you'll see. So the first one we'll look at is the student Bootstrap. And what this confidence interval does is that it tries to increase accuracy by accounting for the fact that we have to estimate the standard error of the Bootstrap samples themselves. So what we're going to do is that we're going to build a confidence interval using critical values from the t distribution. And I'm going to explain how we get those t star values. But you can see the formula here. We're going to get theta hat minus t star 1 minus alpha over 2 times the standard error. And then theta hat minus t star alpha over 2 times the standard error. And we're going to get those 2 critical values using a double Bootstrap. So here's the algorithm. So for each Bootstrap sample, we get an estimate theta hat b. And for each of those, we're going to compute what we call a t-type statistic. So we're going to call it TB, which will be theta hat b minus theta hat divided by the standard error of theta hat b, not the standard error of theta hat. So this standard error is specific to the bth sample. And to estimate that quantity, this is where we do a second level of Bootstrap. We're going to do a Bootstrap on the Bootstrap sample. And then once we have all of those TBs, we can compute the critical values using the sample quantiles from those t-type statistics. And so it's a 2-step algorithm. First, we need to estimate the standard error for each of the theta hat b, And then once we have that estimate, we can compute the TB and then compute the sample quantiles. And as a consequence, what we get is a more accurate confidence interval than the standard normal. But of course, this comes with a high cost in terms of computational requirements. So that's a trade-off. We increase accuracy, but we also increase computational cost. Okay, so let's look at a computation. Here I'm showing code to compute the student bootstrap. And you can see that it starts the same as what we've seen so far. So we have a replicate call, and then we're replicating b times a code block. And the code block starts the same. So first we sample indices using the sample function and replace equals true. Then we can compute row B as the correlation on that bootstrap sample. And so now the next step is to do a second level of bootstrap where so that we can actually estimate the standard error for this particular row B. So you can see inside I have a second call to replicate, and I'm also using a smaller number of replicates here. I'm using only 100 instead of 5,000. Again, this is arbitrary. You could make this a bit bigger if you wanted to, but the cost will be higher, computational cost. And inside that particular replicate or that particular code block, you can see that I'm doing the same as we've done so far. So now I'm sampling with replacement from the indices that I sampled before the replicate call. And I'm saving this into a vector called double_ind. And once I have this, I can compute the sample correlation on that bootstrap sample. Okay, so now what we get is a vector of length 100 called double boot. And again, what we get from this is sample correlations. But now those sample correlations are conditional on the bootstrap sample that we did at first. And those are the samples we're going to use to estimate the standard error of row B. So finally we can compute TB as row B minus row hat divided by the sample standard deviation of double boot. And then finally what we do is that we return both row B and TB as our values from the replicate function. So what we'll get from this is a matrix with 2 rows. So boot row T will have 2 rows and 5,000 columns. The first row corresponds to the row B values, and the second row corresponds to the TB values. So from the row B values, we can estimate the standard error that we would use for the standard normal bootstrap confidence interval. And from the second row, we can compute the T critical values. And so at the top of the slide here, I'm computing T crit vals using the sample quantiles. And you can see I'm only using the second row. And then finally, I can compute the confidence interval as row hat minus the second critical value, so the larger critical value, times the standard error. And then row hat minus the smallest critical value times the standard error. And what we get is this confidence interval, which is actually a valid confidence interval in the sense that it's contained in the interval -1 to 1, but it's much wider than the other 3, and in particular it crosses 0. So all the previous 3 confidence intervals would allow us to reject the null hypothesis of no correlation, but this particular confidence interval would not allow us to do so. Okay. So that was the 4th type. And then let's look at the last one, called the BCA confidence interval. And you can think of the BCA as an improvement on the bootstrap percentile. And So one thing to keep in mind is that BCA stands for bias corrected and adjusted for acceleration. Bias corrected, you can guess what this means. We're correcting for the bias that comes from the Bootstrap percentile. Adjusted for acceleration, I'm not even sure what this refers to, but you can think of this as a second level of adjustment or a second level of correction. Okay, so this one is a lot more involved in terms of definitions. So let's start first by defining capital Phi to be the CDF of the standard normal distribution. And then the BCA confidence interval is defined using the quantiles of the Bootstrap. And then the values at which we evaluate those quantiles, beta 1 and beta 2, are defined as follows. So beta 1 is the image of capital Phi at z0 hat plus this quantity. So z0 hat plus z alpha over 2 over 1 minus a hat times z hat 0 plus z alpha over 2. And then the second level of quantiles, so beta 2, is similar, but instead of z alpha over 2, we have z 1 minus alpha over 2. So z alpha over 2 and z 1 minus alpha over 2 are the critical values from a standard normal. Z hat 0 and a hat I'll define on the next slide. So you can think of those as correction factors for bias and skewness, respectively. So in particular, if you have z hat 0 equal to 0, and a hat also equal to 0, then if I go back to the previous slide, you can see that what we get is capital Phi at z alpha over 2 and capital Phi at z1 minus alpha over 2. So what you get back are the usual critical values that we're familiar with from the standard normal. And so what we would get then is that beta 1 is alpha over 2 and beta 2 is 1 minus alpha over 2. And so the BCA interval would be the same as the Bootstrap percentile in this case. But in general, those values are never 0. Okay, so let's define those two quantities one at a time. So the bias correction factor is defined as the inverse image of 1 over b times the sum of the indicator function theta hat b less than theta hat, right? So we're counting the proportion of theta hat b's that are less than theta hat. And then we're taking the image of that by the quantile function, or the inverse image by the CDF, if you prefer to think it that way. And so you can see how z hat 0 could be equal to 0 if you have exactly 50% of your Bootstrap sample being less than theta hat. Or, in other words, if theta hat is the median of the Bootstrap samples. And so that's the way in which it corrects for bias. And next, we're computing the acceleration factor, so alpha hat or a hat, and we're estimating it using jackknife. So here we're going to do a second level of resampling. We're going to do some jackknife, and we can compute alpha hat as the sum of the cube of the difference theta bar minus theta hat I over 6 times the sum of the squared differences theta bar minus theta hat I to the power 3 over 2. So there's a reason for that particular complex formula, but we won't go over the details of how you can derive this. But just know that theta bar is the sample mean of the jackknife estimates. Right, so for student we needed a second level of Bootstrap, which led to a total of B1 times B2 iterations, right? So where B1 is the first level of Bootstrap, the number of samples for the first level, and B2 is the number of sample for the second level. So it's multiplicative. Here it's a bit different. What we do is we do Bootstrap plus Jackknife independently of one another. So they're not nested. So this leads to a total of B plus n iterations, which is typically less than B1 times B2. And so in that sense, the computational cost of the BCA interval tends to be lower than the student interval. But both of them require a second level or second resampling. Okay, so let's look at an example of computing those quantities. First, I'm going to compute Z0 hat. As I mentioned, what we're doing is counting the proportion of Bootstrap samples less than row hat. So I'm taking the mean to get that proportion. And then I'm taking the image of that mean by the quantile function, which we can get using the qnorm function in R. And as you can see, we don't get exactly 0, right? We know that this is there was a little bit of bias. And actually Z0 hat is negative 0.12 here. Next, let's do Jackknife to compute alpha hat. So as usual, I'm pre-allocating memory, a vector of size n, and then with a for loop, I in 1 to n, I'm removing the ith observation and computing the sample correlation. Okay, and then we can use that to estimate A hat or alpha hat. So first, I'm going to compute the sample mean of my Jackknife estimates. I'm going to call this row bar. And then I'm going to compute the numerator and denominator separately, just so that it fits on the slide. The numerator was the sum of the cubed differences, row bar minus row I. And the denominator was 6 times the sum of the squared differences, row bar minus row I, to the power 3 over 2. And so A hat is the ratio of these two quantities, and we get negative 0.07 or 0.08. So now we can put everything together. The beta 1 was the image of Z0 hat plus Z0 hat minus 1.96, right? The Z alpha over 2, divided by 1 minus A hat times 0 hat minus 1.96. And then once I have that quantity, I need to take the image by the CDF, which we can get using the pnorm function. And similarly, we can compute beta 2. So instead of taking instead of computing the sample quantiles at 0.025 and 0.975, like we would do with the percentile confidence interval, what we're doing instead is doing it at beta 1 and beta 2, which are 0.005 and 0.93. And so we can use those two values to get the quantiles, and we get a confidence interval that goes from 0.32 to 0.93 or 94. And by construction, right, we're using sample quantiles of the Bootstrap samples. By construction, we're guaranteed to be between -1 and 1. So that's a plus for the BCA interval. And if we compare this with the percentile Bootstrap confidence interval, we can see that we get something that's a little bit wider. Sorry, the BCA is a little bit wider than the percentile. But both of them are similar, and both of them lead to the same conclusion, that we can reject the null hypothesis of zero correlation. Okay, so those were the examples. And just to finish, I want to go over the theoretical properties of these Bootstrap confidence intervals, and two properties in particular, which are of interest. The first one is transformation invariant. And what this means is that if I have a confidence interval for a parameter theta, and I transform, I use a monotone transformation, then I want to be able to transform my confidence interval to a confidence interval for the transform parameter by applying that transformation to both bounds. If I can do this, if that's still a valid confidence interval, I say that my confidence interval is transformation invariant. And then the second property is accuracy. And by accuracy, I mean how often, what are the frequentist properties of that confidence interval. If it's a 95% confidence interval, I'm expecting that by repeating this process many, many times, I would expect 95% of my confidence intervals to contain the true value, right? So that's accuracy. So we say a confidence interval is first order accurate if the error that we have goes to 0 at the same rate as 1 over square root of n, as n goes to infinity. And we say it's second order accurate if the error goes to 0 at double the rate, so 1 over n. And you could do third order accurate, fourth order accurate, etc. But the key point here is that we have two levels of accuracy, and that one of them is faster. So as you increase the sample size, you increase the accuracy by twice as much. And so here's a summary of the theoretical properties for the 5 confidence intervals we've looked at. They're not all transformation invariant. So in particular, the standard normal and the student confidence interval are not transformation invariant. But the other ones are, because they're built using sample quantiles. Okay, and then for accuracy, the first 3 we looked at are first order accurate, and the last 2 are second order accurate. But as we've mentioned, that second level of accuracy, second order of accuracy, comes with a computational cost. So that's the trade-off you have to keep in mind. But what I want to point out is that the BCA interval is the only one of the 5 that is both transformation invariant and second order accurate. So my recommendation would be to use the BCA interval, preferably, unless computation time is an issue. In that case, I would recommend using the basic Bootstrap.